Okay, afternoon. I'm Jimmy Haslam, a security engineer at Microsoft, and with me is Bushra Aloraini, a security researcher at Microsoft. We're part of a detection engine team that posts pull request time security and privacy notifications across large established production repos, really big ones. So today we're going to be focusing on a particularly stubborn access control bug called default grant access, and we're going to go look at the performance of two different LLM configurations across more than 183,000 modified methods in 9 repos that we took a look at. So from an engineering standpoint, that's where I come in. The takeaway for ourselves is a bit of a bitter pill. We want to share the bad as well as the good in this house, and Bushra will get to that towards the end of the presentation. However, some of the things we learned along the way will likely be useful for you folks in the audience doing your own detection work. So a few words on context and how we got to be in front of you folks here. Much of our work catches mundane privacy mistakes before merging to main. The developer who logs an unredacted exception object containing privacy information, the customer email that lands in a log pipeline that wasn't supposed to receive it. Everyday bugs, real incidences. The bad ones are pageable by the detection team. They can get pulled in at times. The detectors we ship post comments directly into the pull request, which means false positive costs real developer trust for our team. Developers do not like false positives, of course, so they'll hate you for it. For years, our toolbox was static analysis. Industry-wide precision recall for detecting these issues was pretty disappointing. EASE-24 published a true positive detection ceiling at approximately 11 to 27%. On production code with known volumes in it. Combined tools reached 38.8. Additional custom semgrep rules tacked on top of that push it to 44.7. For our team, the most difficult contextual cases during this era went pretty much undetected, at least automatically. Once LLMs became widespread, we started decomposing the privacy issue detection problem. This meant a static prompt per bug category that included descriptions, positive examples, and counter examples too. And we called such bundle an anti-pattern. Some of these anti-patterns shipped clean, others were noisy. So the hope was to further improve static prompt detection rates with RAG, and we picked DGA as a candidate improvement for 3 reasons. 1, it kept showing up as the root cause in real incident reviews during our postmortems, during team postmortems. 2, it was the noisiest of all the stuff that we attempted to roll out. So we could tease out, so any improvement we could tease out would be most evident there in theory. And 3, OAuth has ranked broken access control #1 web risk every year since 21. A bit more about this fault grant access. We're going to spend 2 slides on this one. What is it? Broadly, it's an access control decision where default behavior is to permit with restrictions applied only conditionally. You see it with permissive initializations. An authorization variable starts at a permissive value like true or admin, and only downstream branch sort of flips it. You see it with permissive return values. A return handler checks when unexpected check is absent. Returns success when an expected check is absent. You see it with broad default entitlements, especially with working with middleware. A wide role is granted at entry and only narrowed in some branches. Overall, the issue is about fragility. If there's an error in logic or a later refactor comes along that breaks things, you want it to be broken in the safe way that denies everyone access to it rather than permitting your private data access to people that aren't allowed, right? So we rather break than give bad access. So here's a very simplified example. In the unsafe pattern at the top, the only thing standing between the caller and access is the is-guessed check, super easy here. Delete that check by accident during a vibe refactor, fail to add a check for a new role that gets introduced, or mishandle an exception line, and implicit auth for access falls right through. The deny first rewrite on the bottom here sets authorization to false up front, grants access only when the user has an explicit role. The failure mode is restrictive instead of permissive. Default grant is easy to spot in this example, but throw in context about middleware, default behavior, context about whether the code handles privacy data at all, and precision recall begins to suffer. We initially explored simple tuned static prompts packaged with few shot examples and called these anti-patterns for default For default grant access, our initial trials revealed that false positive performance for this detection method was not yet sufficient. False positive would have resulted in an excessive amount of developer toil downstream, and our team would have lost developer trust. Important developer trust for us. People don't want their pull requests spammed. It appears that one static example set couldn't simultaneously cover Java, C#, C++, and TypeScript. So we tried something new. We tried looking into RAG. Instead of one fixed set of examples, we would retrieve a bespoke few-shot set during an embedding search against a curated knowledge base of real-world incident distilled examples. Ideally, each piece of code under our review would receive examples that would be most appropriate for coming to a bug, no bug determination. It was language matched as well. We'll talk about that. We could have shipped this after a smoke test, but we didn't. In this house, we make data-driven decisions. RAG carries real operational cost, knowledge base to curate, an embedding model to maintain, a drift to manage before paying that cost in production. We wanted to know whether RAG actually earned its keep at scale. Default grant access was the track on which we conducted that foot race between static and RAG. We want to share some of the results of this engineering decision with you. It was really, this is a really sort of get your hands dirty engineering decision. And we wanted to answer two questions. Does retrieval-augmented generation improve detection quality, precision, relative recall F1 compared to a standalone prompts? Or how does the answer change across programming languages? We chose Java, C#, C++, and TypeScript because they are the most common, four common languages that our particular organization generates. It's C and AI in Microsoft, by the way. Holding the base model and task instructions constant lets us isolate retrieval as the only variable. Same prompt, same scaffold, same output format, same adjudication. The question is whether the source of examples alone changes real-world detection behavior when we examine it at scale. So the comparison, both configurations use GPT-4. So this would have been last year we made this decision. The same task instructions, the same evaluation corpus. The only difference is where the examples came from. The example LLM gets 5 static examples, 3 positive DGA instances, and 2 counter examples, all written in C#, regardless of the target language coming in. The RAG configuration, on the other hand, 5 positive and 3 counter examples from the knowledge base, matched by cosine similarity plus language match to the query. So incoming code to analyze was in TypeScript. So the examples and counter examples are also TypeScript, unlike the static stuff. But overall, same model, same scaffold, and we varied the examples. The knowledge base held 84 curated examples for DGA, indexed in Azure AI Search using OpenAI's text embedding 3 model. Each example was taken from a real-world incident and rewritten in each of the 4 categories by engineers fluent in that language. So not a mechanical translation, so we use human misery. There's a lot more of the human misery. One important caveat up front, Java and C# drew on the richest pool of incident data. TypeScript and C++ examples were translated by hand at times from real-world examples. So using RAG to review the code, of course, it's not a particularly new idea. 3 things separate this particular implementation that we're looking into from a generic code review pipeline that we would like to call out at this time. First, our knowledge base is built from postmortems that we've encountered in practice going back years now, 50 years almost at this point. Those examples carry context about our own code that general retrieval from the internet does not. Second, we don't ask the model, is this similar to known bad code? We provided the prompts the same criteria that ground truth human reviewers would use when we did the manual misery validation of this study. We validated all this stuff by hand, so a lot of human misery to come to these numbers. This includes instructions on how to make judgments on contextual issues and not just similar code. And third, counter examples are first class. 3 out of every 8 retrieved items are negative examples, and without them, we would get a much higher false positive rates when encountered. And so to talk about the numbers here, I'm going to hand it off to Bushra, and she'll talk about what we encountered here.
Thanks, Jimmy. So next question, does retrieval actually helps in practice? In order to find out, actually, we run our analysis on a repo, production repo, across C#, C#, Java, and TypeScript. So what we did, actually, we analyzed the repos for 30 days, and we actually looked at each pull request, and we looked at each modified method within that pull request. We ended up actually analyzing 183,000 methods totally, and in total we have 145 findings by both RAG and LLM. RAG actually produced 100 detection, while standalone LLM produced 45 detection. All the 145 went through manual review with 2 actually subject matter experts. If there is disagreement between the 2, of course, we have a tiebreaker. One thing I would love to actually mention is that we had a limitation. We don't really know the true recall. We don't know how many default grant access actually in our corpus. And also, we didn't sample negative examples, meaning we didn't actually look at method that was deemed to be safe by LLM and RAG, but they are not. For that reason, actually, we actually used something different, a relative recall. So we took all true positive from all detectors and actually used them as a proxy of coverage. So did actually retriever help? Well, actually, RAG produced twice as many verified default grant access compared to LLM. If you look at the relative recall, you can see the relative recall actually improved from 38.8% to 77.6%. When you look at the findings by both systems, we expected that RAG actually produced just more bugs, the same bugs and more, but in fact it was different. So RAG and LLM produced kind of distinct bugs. There is a very limited overlap. There is only 16% overlap between the actually 2 detectors. Now look at the precision. The precision went very down. It was very unexpected. Actually, the reason we implemented RAG is that we wanted to improve precision. But in fact, our result shows actually it was the opposite for some languages. In order to understand why, we looked at these numbers language per language. So here's the table. It shows language. It shows the system. We have also the precision, relative recall, and relative F1 score. A relative F1 score actually measured the harmonic mean between precision and relative recall. Look at recall column. You can see that recall goes up every single time, every single language. Precision, there is a split. Some languages, precision improve, and other actually precision decreases. For Java and C#, precision improved. C# actually had 90% precision. And if you look at F1 score, 0.79, 0.78, these are kind of good numbers, are not reaching our quality bar, but we can go there by improving the detection. TypeScript, it's always terrible, whether it is LLM or RAG. So it doesn't really matter what language, what kind of method we use. For C++, it was kind of surprising. The precision actually went down from 50% to 28%. So why is that? We believe that it has something to do with how ecosystem actually express authorization. Looking at the true positive detections, we can see that in Java and C#, there is a clear authentication marker, authorization marker, such as attribute and annotations authorize. That can really help the retrieval. For TypeScript, when you look at the detections, majority of the methods actually resemble default grant access, but they are not, in fact. For C++, we saw multiple methods actually handle low-level operation. They really used some vocabulary of authorization, but actually they just access the resources. One thing we would love to actually also highlight is that because our knowledge base was really inspired by C# mostly and Java, that's how it actually reflected in the precision. That's why we see precision in terms of C# and Java were the best. So now that's about recall precision. Now let's talk about cost. And I would love to actually talk about cost and compare LLM RAG compared to traditional static analysis. We do usually think about cost in 3 actually terms. First, the runtime cost. Of course, LLM very expensive. RAG actually even more expensive. And static analysis is really cheap and very fast to run. So static analysis wins this actually factor. The other factor is the coverage. Now static analysis really struggle. Struggle with the contextual anti-patterns such as default grant access. So here in that case, LLM win. And if you actually miss an opportunity to detect a bug, it will be actually end up into production. It will be incident, privacy incidents, and it will cost us a lot. The third thing is precision. So the cost per usable findings. If you have very low precision and you actually waste human times, especially if it's developer or human reviewer, by the end of the day, you will lose trust and they will ignore everything, even though it has huge recall and coverage. So it doesn't matter. So the question here is that, is it more findings worth it without precision or better precision? So do we surface the system? In our case, we did actually not, and that's because our persona are engineers, and precision very critical. However, if we have security actually researcher, they would really appreciate recall over precision. They have their own tool for pre-filtering and actually improving the detection. So it really depends on your actually end user. And I would love to actually end up with our lessons we learned. So RAG is not actually something can be helpful all the time. Sometimes it can help, sometimes it hurt. Also, that depends on the detection and the framework we are using. If your framework have vocabulary or labels or conventions, then it will improve your detections. Also, knowledge base actually really matter. In our case, we saw precision was very nice in C# and Java, and that's because actually knowledge base was inspired by C# and Java incidents. Finally, Retriever is a tool, not a universal upgrade. Thank you so much. We were happy to take your question now.